All right, welcome everybody. My name is Kem Tekinay, and I'm here to talk to you about encryption and using encryption in your database. What we're going to do today, so we're going to review the basics of encryption because there's a lot to know to be able to use it properly. And then we're going to talk about how to encrypt data in your database, retrieve it. I'll show you, if there's time, I'll show you the code to actually make that a little easier, and how to search on it. Now, I want to point out that I am not a security expert by any means. What you're about to see is a product of many hours of research, and this is after I did things the wrong way, and then fixed it and did it better, and then we still have to do it even better. And so this is just some ideas I want to share with you of solutions I found to solve some of these problems. Along the way, I created an open source project, or if Tim was here, something he'd call free, called Encryption, which is actually a port into Xojo, pure Xojo code of AES, Blowfish, scrypt, and bcrypt, and that's available. I'll give you the link at the end, but we're going to be using that as part of the demo. So let's get going. Okay, so what are the goals and assumptions of our session today? Well, one of the goals is we want to protect data at rest. In other words, you have data in your database when it's not actually being used by your app, browser. Someone who's just casually looking at it should not be able to decipher the data that you have in there. And by the way, we're not talking about encrypting all the data in the database. We're talking about encrypting the sensitive data in your database. You have patient names, credit card numbers, stuff like that. One of our goals is compatibility. Whatever we choose, we want to be able to make sure it's compatible with a wide variety of tools, not just our own apps, because you never know when you might need to work with the data with using some other tool. The assumption is that whole database encryption is not available. You can't set a password on a database to have it encrypt the whole thing. So that would include Postgre, MySQL, and SQLite. Now, some of you might be thinking, well, wait a second. Of course you can encrypt a SQLite database. There's a setting right there in in Xojo. It's a property. You set the password. What's this guy talking about? I should have gone to talk about color with Chris. Yes, if you can use SQLite's whole database encryption, that's better than anything I'm going to show you today. It's convenient. It's fast. But what it's not is compatible. If you open such an encrypted database in a tool that was written by Xojo, no problem. But if you open it with a third-party tool, you're probably not going to be able to get to the data. It's probably not going to recognize it. So if you want to keep compatibility with other tools, then we're including SQLite in this list. Finally, usability is important because encrypting the data that you can't actually use is not going to be good for anybody. So those are our goals and assumptions. Now, let's talk about some of the terms we'll be using today. First, when we talk about encryption, we're talking about the algorithm that we're using, and there are actually quite a few out there. You can go to Wikipedia and look it up, and you'll see a whole list of things. But the main ones we're going to be talking about are AES and Blowfish. Interesting thing about AES, as an aside, I'll tell this story. The government standard for encryption used to be triple DES. Does everyone remember that? Yeah. They realized that was getting long in the tooth. They had stretched as far as it could go. Technology was catching up. It wasn't going to be good. So they held a contest. Who could come up with a better algorithm? And there were various submissions, of which one was, and I'm going to mispronounce this, Rijndal. Does anyone know how to pronounce that better than I'm pronouncing it? The answer is no. So Rijndal and Blowfish. Rijndal won. That became the AES standard, of which now there's commonly three variations, AES 128, 192, and 256, and that refers to the key size, which we'll talk about. Blowfish did not win, but I guess it was people who looked at it said, well, this is a pretty good algorithm. We should use this. And so it's become very common to use Blowfish even though the guy who developed Blowfish doesn't understand why it's common, why it's still in use, and recommends against using it. He actually came up with Twofish, which is a better algorithm. Having said that, as far as I know, neither one has been broken. So if you want to use Blowfish because it's convenient, go ahead. But for our purposes, we're going to be concentrating on AES here today.
Does that affect what we're doing? In other words, can we do what you're going to talk about using Blowfish?
The question is, does the algorithm, your choice of algorithm affect any of the ideas I'm going to be presenting today? And the answer is no.
Great, thank you.
Okay, other terms we'll be using today. Password, the key, the mode, and the initial vector. Let me get to all of these. Password versus key. A password is what you commonly come up with when you go to your favorite recipe site and they say, enter a password and make sure you only use uppercase, lowercase letters, and these symbols. It's text, it's human readable, it's something you'll remember, and it's of unknown length. It's whatever you come up with. And usually there's a limit for whatever site you're on, but there doesn't have to be. The key is what the algorithm expects. Now, these terms are often used interchangeably, and I'm guilty of that as well. But the key is actually bytes. It's not text. It's raw bytes. It's of a fixed length, which means the algorithm actually expects a certain length for the key. And AES will actually stretch a password into that length if you don't supply it the right length. And it can and will be derived from the password. As I said, AES will do that for you, but you can also use a hashing algorithm with a salt to derive the key and other information. We'll talk about that in a bit. The mode. Just by show of hands, how many people have heard of mode when it comes to encryption algorithms? We had about 4 or 5 hands raised. There are 2 main modes. There is actually quite a few modes when you get into these algorithms, but there's 2 main modes that most software recognizes. One is electronic codebook, and the other one is cipher block chain. Now, out there in the real world, nobody calls them that. They're always just ECB or CBC. So that's what we'll call them. What's the difference? The ECB does not have an initial vector, which we'll talk about in a moment what that is. And same data means same encryption, which means if you take, in ECB mode, if you take a block of data, and by the way, these algorithms always expect a certain fixed block. They work on a certain fixed block size at a time. AES works on 16 bytes at a time. So the same 16 bytes will always be encrypted exactly the same way. The output will always be the same with the same key. CBC uses an initial vector, and with the same data, it's different encryption because the first block of data determines what the encryption of the next block of data will be, and that will determine what the next block of data will be, and so on down the line. As an example, this is 0 through 7 repeated twice to make up the required number of bytes. And it's encrypted with Blowfish, which is an 8-block algorithm. And the password is just password. Now, you can see with ECB, because it's repeated twice, the output is repeated twice. But with CBC, the first block is exactly the same because I didn't use an initial vector. And then the second block is different. The way it actually does that is it takes your data, encrypts it, then takes the encrypted data and XORs it against the next block of data before encrypting that, takes that, XORs it against the next block of data, and down the line. So the data will look different all the way down. What's important about this is so that something encrypted with CBC, you can look at a whole page of data and won't know if anything is repeating. Now, I mentioned the initial vector. Again, used in CBC mode. It's a fixed length bytes. It's actually equal to whatever the block is that the algorithm expects. So AES works on 16 bytes at a time. The initial vector is 16 bytes. Blowfish works on 8 bytes at a time. Initial vector is 8 bytes. Which I jumped ahead, but that's what that is. And that's a scrambler, which I just described to you. And one of the keys to the initial vector is it's not secret. So how does this work? I just said when you encrypt the first block of data, that encrypted data is used to XOR and scramble the next block before it's encrypted and down the line. But the first block of data does nothing to scramble against. So you supply something. You pick something randomly. Doesn't have to be secret, because none of the rest of it is secret. Anyone looking at it would see that what the vector is for every subsequent block. But that whatever bytes you supply, that's used to XOR the very first block, and then that's propagated down the line. So let's see this in action. I have here a little app called Picture Encryptor. This actually encrypts a picture in the two different modes. And the first mode is CBC, which, as I mentioned, encrypts the first block and then uses that to scramble the next data and down the line. Can anyone tell me what that's a picture of?
It's my house.
No.
We got my house, snow.
Yeah, there you go.
OK, what the original picture is of. So let's look at the same data encrypted with ECB, which, again, same data is always encrypted the same way with the same key. Can anyone tell me what that picture is now? Yeah. And
Some sort of deep sea.
of course, that's the original. Now, that's why it's when you encrypt, use CBC. You want to make it as difficult as possible for a bad actor to glean anything about the data, and that will help. Going back to CBC, you notice down here it says IV none. This is not supplied initial vector. So actually, this very first block of data, you could probably tell, is the same as the ECB encryption. Yeah.
Oh, yeah, that's right.
Yeah, but every time I press it, it actually picks a new initial vector. So you see what's happening. Even though it looks like snow, it looks like different snow each time.
It's different snow.
Right. So you could take this same picture with different initial vectors with the same key, and it would look like different data. Did anyone have any questions about that before I proceed? OK, good. OK, so before we get into how to use this in a database, here are some tips for encryption. First, do it yourself. Various databases will offer tools to encrypt. Our database of choice is Postgre. Postgre has the ability to encrypt in CBC mode using AES or Blowfish, supply an initial vector. We never use those tools because in order to use them, you must supply the key to the database. And if you do that, that query could show up in a log somewhere, and which means your key is there in the log in plain text, and you've defeated the whole purpose of the encryption. So do it all in code. Anything that goes into the database should not know how to decrypt its own database. It all should be external. Secure that key, of course. Well, this is probably off topic, but don't supply that key. If you're distributing an app, don't put that key in the app, even obfuscated, because somebody is just going to reverse engineer the app and gain the key and gain access to all your data. And there are techniques to doing that that are outside the scope of this session, but it's just something to think about. distinguish your encrypted data. When you store it, first, you could choose to store it as binary. You probably don't want to do that. Store it either hex encoded or base 64 encoded, but distinguish it in some way so at a glance you can look at it and say, that's encrypted data. In that way, you could actually embed encrypted data within plain text, and you could still pick out that encrypted data and decrypt it. The format that we like is, you see this prefix, $ENC$, that's not going to appear in the wild anywhere, followed by the actual data, followed by the vector that's used, the initial vector that's used to encrypt this data. Use middleware or user-selected password. This goes back to what I was just saying earlier. You don't want to distribute the password that's used to decrypt this data to your users. Does anyone here not know what middleware is? OK. So nobody raised their hand. That's funny, Jeremy. If you're using middleware, you can secure the key on the server itself. If you must distribute your app, let them pick the password that will encrypt the data, or do something else where the password is not distributed.
So how would you use middleware to
The question is, how would you use middleware? So middleware sits on a server and is the conduit between the database and the users. So if the middleware is decrypting and fetching the data, the users never see it. The users are making requests to the middleware is handling the data transfer and returning it to the users. Does anybody else have any questions before? OK. Use a secure key. The data is important enough for you to want to encrypt it. Don't pick something like password to encrypt it. I don't think I need to say anything more about that. Yes, the suggestion is admin. A much better password. So what we're looking for here is a balance between usability and security. Most databases, when you design it, perfectly usable. There's no encryption. The data is all in plain text. It is as usable as you can get, but there's absolutely no security. On the other end of the spectrum, I can tell you how to achieve, well, that says 100. You'll never achieve 100% security, but you could get pretty close. And I can tell you how to do that if you sacrifice usability entirely. So we want to find a balance somewhere between, and that is what I'm going to present to you now as some ideas of how you can achieve that balance. Any questions before I show the demo? That's a good crowd. OK, so let me actually get rid of this. We don't need this anymore. I have here a SQLite database. Oh, I resized that on the fly, and I did a good job. Wow. This database is essentially of people. There are 4 tables in here, which I will review, not all of which would be used in production. The main table is this one, person. Person has a first name, last name, city, state, zip, and a credit card number, which I faked. This is what will store your encrypted data. This reference table here is a one-to-one corresponding record of the unencrypted data. You wouldn't use that in production. We're using it here just to show what the unencrypted data would look like for convenience. Meta, I'm going to get back to. I'm going to circle back to that. Vector is a very small table of initial vectors that we use. These were all picked randomly, stored in the database, and this is what these are the initial vectors that will be used to encrypt every bit of data. The password will be the same. The initial vectors will change among these 10.
is just an arbitrary number.
Absolutely arbitrary. I did it here for testing. I actually tested with 20, and I still got good performance. So the more initial vectors, sorry, I should repeat the question. The question was 10 an arbitrary number? The more initial vectors you have, the more differentiated your data, your encrypted data will be, so the better it will be, but you will sacrifice performance, as you will see. Try to find a balance. If you don't need to search the data, don't use a table of initial vectors. Pick a random initial vector when you encrypt the data. You don't need to search it. You just need to retrieve it. If you store it the way I showed earlier with that encoding, doesn't matter what vector you use for it. It's going to be decrypted anyway. So I have here, so I go the right direction. OK. I have here an app that will actually let us explore the data in this file. I'm going to jump right here to show you, and everyone can see that, right? You all see that in the back? Yeah. OK. So let me reset my query. So here is the person database. It's actually 100,000 records, of which for performance purposes, I'm only showing 1,000. When we look at the reference, this is the original raw unencrypted data that was ultimately encrypted into the person table. You'll notice the difference between the reference and the person tables. Reference is mixed case. Person is uppercase. Why? If you need to search this data, you need to know what the case is going to be. There's no way to search encrypted data if the case is mixed. You can guess at what the case would be, but your searches are going to be off. So you have to uppercase it. Now, I came up with an idea that would let you retain mixed case if you want to. That's not for this session. Come see me after if you have that question. This is what the raw data actually looks like in the person table. And just to stretch that column a bit, so you can see there's that ENC prefix to tell us that it's encrypted. Here's the actual data. And there's a $, and then here's the initial vector that was used for this actual data. And these initial vectors were pulled out of that vector table that I showed you earlier. At the time of encryption, those vectors were chosen purely randomly. If you guys don't know, in the crypto module, there's get random bytes. That will get you random information in a secure way. So that's cryptographically secure. So if you want to keep your stuff cryptographically secure, make use of that get random bytes.
So these vectors here aren't part of your set of 10.
The question is, are the vectors that are displayed here part of the set of 10? Yes, they all are.
So why not use just a pointer rather than store the whole vector?
You could do that. Okay. For illustration, for this demo, the question is, why didn't I just use a pointer instead of storing the vector? And the answer is you could do that. Just make sure you don't lose that vector table then.
Right.
I got another question here. Kimball.
Just quickly, you've got a $sign to separate your data from your vector, but since your vectors are all known and they're all the same length, is there any real reason to have the $sign? Could you just say my last 16 bytes are the vector?
The question is, why did I choose this format, and why am I using two $signs instead of just saying, well, we know the last 16 are the vectors, so why not just pick out the last 16 hex digits here? The answer is you could, but then you make sure you don't change your algorithm later on or make note of what algorithm you used. But if you make note of what algorithm you use, you potentially give a bad actor more information. So I chose it this way because chose to do it this way because at a glance, I wanted to see exactly where the vector started. It also makes it easier for me to say, hey, the vector starts right here for you guys. So, OK, so again, have a bunch of names. There's the unencrypted data. There's what it looks like after it goes through the encryption process. Let's run a query on these. So let's find everyone whose first name starts with Edward. And roughly, this is what we're looking for. So select star from person where first name equals Edward, and we're limiting to 1,000. So I'm going to look at the reference data first, and this is what we are actually looking for. This is just running a pure regular SQL statement on the reference data to show what we expect to find. What we actually find is identical. And again, there's the raw encrypted data. So how did we do this?
That's a good question.
Yeah. This one was actually pretty easy. We already know what the vectors are. We know what we're looking for. So we take what we're looking for, we encrypt it with all the vectors, and we say where the first name is in that set of data. And any SQL engine happily complies.
That's cool.
The question was, that's cool, and the answer is yes.
But if you're doing a lot of complicated joins, this query is going to get real messy real fast.
If you're doing a lot of complicated joins, you're going to have to, the question is if you're doing complicated joins, is this going to get messy? And the answer is probably yes. And so you have to do a lot of experimentation. And there are probably techniques where you could create sets of your data. So maybe use with clauses to pull out the people and then join against that. I'm sure there are ways that you could do it. That's outside the scope of what we're doing here. OK. Let me look at the reference and let me pick somebody. Edward Jung. We'll say Jung. I'm not sure if I'm pronouncing that correctly, but that's a nice short one. So we are going to look for Edward Jung. Again, look at the reference. That's straight SQL. Finds that one. We look at the person. Finds that. And you can imagine what that SQL looks like. So we're just looking for first name is one of those, and last name is one of those. Conceptually, does this make sense to everyone? Anyone have questions about this? OK. Let's reset the, let's not. Let's now clear that. Now let's get a little more complicated. We want to find anybody whose first name starts with Ed. This is what we're looking for. There's actually 415 records, so it's within our limit of 1,000. And you see that this straight SQL query, 0.04 seconds. And there it is in person also. Still 415 records. This took longer, 0.324 seconds.
8 times longer.
But reasonable. That's the balance between usability and security. And by the way, this is SQLite, and other engines will be faster. Anybody want to venture a guess how I did this? Not a hand. I'll show you. We're going to go back. Remember let me clear this query for a moment. Remember the meta table that I mentioned that we're going to look at later? The meta table is just this. It is a raw table of every bit of information that we might be querying against, completely in a random order, not connected to anything else, seeded, so there should be more data in here that actually exists in your database. But that still covers all your encrypted data that you want to do a contains search on. I want to do a like query against. Any of the data that you put into the meta on its own should be useless to anyone. Someone's first name, someone's last name, a city, a state, even a street name, useless on its own. You can't connect it to anything. Credit card number probably would not be a good candidate for meta.
You know, Kem, but thinking of that, with the credit card number, you would never search based on credit card number, so there would be no reason for it to be.
Jeremy's jumping ahead and saying with the credit card number, there'd be no reason to search against it. He's absolutely right. You might want to search for a credit card number, but you never do a like search on a credit card number. There are other bits of data that you might want to do a like search that this technique is not going to work on because you don't want it listed in plain text anywhere.
So this is plain text.
The question is this plain text? Yes, this is just plain text.
Okay, keep going.
Okay. So how do we do it? I want to look for any person whose name starts with Ed. And by the way, you notice this time, 0.09 seconds to do that, to run that query. What does that SQL look like? Well, that SQL looks like this.
Oh, good grief.
So what did it do? The code recognizes that we're doing a like search because it has it has the %sign in it. How am I doing on time? Good. The first thing it does is look through the meta table and pick out every meta that starts with Ed. It then turns around and encrypts each one of those items against every vector. And by the way, you see why I only use 10, because if I use 20 or 30 or whatever, we'd be here for a while.
That is still way cool.
Creates this.
Yes, that's what
Oh, thank you.
How does the database query optimizer deal with this kind of stuff?
The question is, how does the database query optimizer deal with this stuff? The answer is I have no idea, but pretty well, because if you look at the query 0.088 seconds, as opposed to when we look at the reference 0.013 seconds. So, any questions as to what Kimball?
Just one quick clarifying question. If the patient, or not, sorry, I work in medical stuff, so I just use patient.
That's fine.
We're all patients, Steve.
Yeah. If the person's name was, say, Mark, and you wanted to search for anybody whose name contained ARC, this would not work.
Kimball jumped ahead and asked if we wanted to do a contained search instead of a begins with search, will this work? The answer is yes. I'm going to show you that soon.
Okay.
The metadata is all the data from all the other, from your other tables just in one column.
The question is the meta table all the other data that you might want to search against combined in one column? The answer is yes. OK, so now we want to do where the last name starts with J. Now we found 7 records in 0.013 seconds. And we found those same 7 records in 0.163 seconds. Again, there's a trade-off in performance, but it's not. This could take a few seconds, and you'd probably still accept it. But in fact, it is actually pretty quick. What does that SQL look like? Well, as you might imagine, it's the first name in any of those, because it's doing the meta that starts with ED. And eventually,
So that's a
well, I'm not going to.
by every metadata.
I think. Oh no, that's just long encryption. Well, I'm not going to find it, but the meta that it actually found with the first name starts with ED and the last name starts with J, it's all combined here just for display purposes. But in your code, you would actually pick it out and say, show me the meta that starts with ED, encrypt it against those 10 vectors, create the SQL statement that says first name in that, show me all the meta that starts with J, and repeat and say last name is in that. And you end up with that query, which again runs pretty quickly. Now the question was, what if you wanted to do a different type of like search? So let's say starts with ed but ends with IS. And Kimball, I know that wasn't exactly your question, but we're going to do this one first. So let's see what we find here. OK. Found 11 records. First name starts with ED. Last name ends with IS. And we look for the person. it found the same record. 0.09 seconds, 0.01 seconds. The query is exactly the same thing. All it's doing is querying against meta. So it doesn't matter whether you're doing a starts with, ends with, or contains search. It's just going to find the meta and construct the same in statement.
Okay. So to summarize, basically,
That's my job.
when I do a query, I first query the meta on what I want,
Right.
and then I do that kind of craziness against that subset of meta.
The question is, in summary, do you query the meta and then construct this huge in statement against that meta? Correct. That is exactly what you do.
Okay, very neat.
Kimball.
So with respect to performance, then you've been showing us very reasonable performance for executing the constructed SQL. But how long does it take to construct that SQL in the first place? Is there an additional performance hit that's
The answer is constructing the SQL taking up time and impacting performance. If it is, I haven't detected it.
You're doing it on the fly here.
I'm doing, yeah, absolutely. Yeah, you guys could holler out things for me to query against. The question was whether I'm not doing it on the fly, and the answer is absolutely. Just to answer Kimball's earlier question, we're going to do a last name that contains SA. And we found 9 records in here, 0.011 seconds. Same 9 seconds. This took longer, 0.228 seconds. And the reason it took longer, I'm sure, is because it found 1,344 meta records. Again, it doesn't do all the meta against each column. It only picks out the subset of meta that's interested in, encrypts those against each of the initial vectors, and then queries against that. Anybody have any questions on that?
Okay, I might have a comment.
Go ahead, Jeremy.
In practical use, people don't search for a name with just SA.
Yes, the comment is that in practical use, people don't typically do a contains search on a name, and that's right. In my experience, they'll do a starts with search, if anything. You get a name, you say, well, show me Jim or James, so let's get a name that starts with J. You don't do a search for a name that ends in MES. However,
Part number, though.
yeah, there are some, there might be a part number was the comment, and there are some bits of data that you might want to do a like search on, and so it's good to know that it actually performs. Yusuf.
So if you were doing, obviously the aim of this is to desensitize the data, so it works well with first name, last name. In fact, nothing would stop you filling your, if you only had 10 people and you wanted to disguise those 10 people, nothing would stop you having a meta table which already had 1 million first names in it.
The question is, should you seed your meta table? And the answer is absolutely yes.
So that way you wouldn't know who's actually in the database.
Correct.
Just
You wouldn't know.
Reference.
Correct. You wouldn't. You shouldn't be able to know from looking at the meta table whether any of those records actually exist in your database.
Yes.
And it doesn't matter if it does or not.
Yes, you could do the same with dates. You could assume, take
Correct.
all the dates since
You could do the
year
same
dot and
comment
just
was you could
fill
do the
them
state.
to start with.
And in fact, the city, state, and zip is the easiest because you can just fill in the entire database of city, state, zip for those of you who are working in the US or whatever your nationality is. You put everything in there, it'll search against, it'll query against the meta, and then construct the SQL.
So what would you do with something like email address?
You wouldn't. The question is, what would you do with something like email address? Again, that is something that you could connect to a person, and you wouldn't put that in
Just think
the
of
meta.
a scenario where you've got,
But-
obviously these kind of uses are where you've got somebody answering on the telephone, somebody says, hi, I'm
But-
Kem, what's your email address,
But that actually transitions into this. So let me pick a CC number here, 1901, 1769. 1901, 1769. So there's a very brief credit card number. That's referenced. That finds it. One person. And it finds it here. Because this never hits against the meta. We're doing a direct query
It's a full
on the
one.
data.
Yeah.
So we just encrypt it against all the vectors and do a in.
Yeah, so sensitive data, you just ask for the full lookup.
Correct. You search against the whole thing. And with something like an email address, that's what you would do. If I change this so it starts with query, the reference still works because that's just straight SQL. Person doesn't find anything
Because you haven't populated.
because there's nothing in the meta that it can search against. Okay, any other questions?
Yeah, I came in a little bit late, so I might have missed it, but what is the value of
All right, let me start again. Sorry.
what's the value of having multiple vectors? What's the purpose of that?
Oh, that is coming in late. That's something we reviewed. The question was what's the value of having multiple vectors? Come find me after, and I'll recap for you. Any other questions?
Again, with
Kimball.
multiple vectors, you mentioned that having 10 was a nice kind of compromise between security versus performance.
Yes.
How much worse does your query performance get as you go to 20, 40, 100 vectors?
I only tested with 20. I didn't notice much of a difference. The longer the query is, obviously. Oh, and of course, needless to say, each of the columns I'm querying against are indexed. So the SQL engine is going to optimize with that also. Did I repeat your question?
Nope.
Oh, sorry. The question is, what's the impact on performance with the more vectors that you include? And the answer is that I didn't detect much when I went to 20, but I didn't go beyond 20. That's something you should test to discover. But each of the columns are indexed, so the SQL engine will do some optimization for you. Any other questions? Okay. You guys all get how this works. I've only got a few minutes left, so let me see if I can review some code here. Whoops. Let me do that. Okay. So to make this easy, here's the actual code. And obviously, this is for demo purposes. I've done some stuff here that I wouldn't actually do in the real world, but for demonstration purposes, to make it easier to follow, I've done it here. I have a very limited ORM called person with a bunch of properties that correspond to the columns. CC number, city, first name, so on and so forth. There is also an encryptor, which is an encryptomatic. An encryptomatic is a subclass of my AES, class. I believe I set this to AES 256. And the encryptomatic, aside from the functions and methods that the AES class has two simple functions: to database and from database. When the person, let me go here. When we want to save a person, a new encryptomatic is created if one doesn't exist. If there is no ID for the person, then it's going to do an insert. Otherwise, it's going to do an update. And those will run the columns through the encryptomatic, calling the to database functions. The encryptomatic knows where to get the vectors. It creates the data to store, and that gets stored in the database. When it pulls it out from the database, the reverse process happens. Now I've got to find the code that actually does search. OK. Very quickly, and anybody who's really interested, come find me and I will show you this code. Or, as you know, you'll get this project at the end. Dana will make this available. So this is the code that actually creates the SQL statement. And you see there's not much here. There's an append to where, which gives it the column name, the information, and what encryptor to use. And append to where will figure out whether you're doing a like search or not. If you are doing a like search, it'll pick the value out from the meta. Otherwise, it'll just do straight encryption on the value you're searching against and construct that where clause. This is actually very simple Xojo code, and in 64-bit aggressive, which is how I have this compiled, it's darn quick.
Isn't that going to fail if you have a % sign in your name?
The question is, isn't this going to fail if you have a % sign
In what you're searching for?
in what you're searching for? Yes.
Okay.
Don't do that. Again, for demo purposes, there are things that I didn't cover, but those are certainly things you should think about for your own projects.
It's true in any SQL, though.
That's true in any SQL is the comment, and that's right. Does anybody have questions on this code in my 4 remaining minutes? OK. Let me pick up on my presentation then. OK, so in constructing this meta table, here's some tips. First, no ID. That makes it a little tricky in SQLite, easier in other engines like Postgre, which doesn't automatically assign an ID to records. There are ways to work around it, but the point is you don't want a bad actor to look at the meta table and determine anything about your actual data, including order. If you're inserting a bunch of records and you have an ID and you see that this record was inserted on ID 100 and this record was inserted on ID 101, you could probably figure out what it belongs to. You want to avoid that. You don't want any logs of the meta being inserted for the same reason. You don't want to be able to attach the meta to the real records. And that goes back to independence. You want to seed the data. So there are plenty of lists out there on the internet. I actually use, to construct my data, I use lists of first names and last names, and of course the database of city, states, and zips. The more data you throw in your meta, the better. As long as you shuffle it. You should shuffle it periodically. You should shuffle it after every update. You should shuffle it after every insert. It doesn't have to be a complete shuffle. What we do is, when we insert a patient, because we also work with patients, on an insert, it randomly picks between 0 and 50 meta items from the table, deletes them, and then reinserts them at the end. Once something is inserted, you don't know how much data was inserted after it. Every day, the whole table is shuffled. By the way, shuffling the table, it's in the project also. I didn't show it, but shuffling the table is load all the meta, run it through shuffle twice if you want to, drop the table, recreate it, and put all the data back. OK, some encryption tips. I've got 30 seconds. You don't want to create an oracle. This is a term used in encryption. It's very simple. Your app is encrypting this data. If somebody can use your app to encrypt their own data, you've created an oracle for them. They can say to your app, what would the encryption look like for this piece of data? And using that information, they can pick out other pieces of data. Don't do that. Don't have that in mind when you create your app, that you don't want somebody to be able to do that. If you have no need to search the data, use a random initial vector. It doesn't matter. It's only for display purposes.
If we don't need to search, do we need to feed the meta table?
If you don't need to search it, the question is, if you don't need to search, do you need to feed the meta? And no, the answer is no. It doesn't have to be in meta also. Where's Tim? Tim in here?
He stepped out.
He stepped out. Good. So until he comes back. Use get random bytes. I've already mentioned. salt and stretch. You know what? Let me do this quickly. For data that doesn't have to be searched and you really want to secure it, take your key, take your password, use a random salt and run it through an algorithm like scrypt or pbkdf2 and stretch it to the number of bytes that you need for both the key and the initial vector. So for AES, that would be 48 bytes. The first 32 bytes is the key. The last 16 bytes is initial vector. Store your initial vector. Use that key to encrypt the data. I'm sorry, you don't store the initial vector. Use the initial vector. Store the salt. If you run the salt with your password through the same process again, you'll pull out the same key and the same initial vector. And that's what that looks like. So hash the password in the salt to get the key and the initial vector, encrypt with the data with the key and the initial vector, store the encrypted and the salt. That's it. Any questions? Fred.
Have you done this in production with a long-seated meta list with a large database, tens of millions of records?
We have done it in production. We have not used multiple vectors yet. We're using a single vector. And Jeremy, how many patients do you think we have, or Eugene?
We have about 1 million.
We have about 1 million patients. We have no problems with performance at all. Any other questions? All right, that's it. Thank you for coming.
The price of admission.
By the way, for anyone who's interested in Encrypto, it's on my GitHub account. It's right there.